Bismillahirrahmanirrahim, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will discuss the interpretation of the transformation matrix C. And we know that I3 is equal to D3 ID, I4 is equal to D4 ID, where ID is the total load current. And D is called system load center, and D is a hypothetical node. So these four currents I1, I2, I3, and I4 can be expressed in terms of I1, I2, and ID. And since I1 is present at both sides of this matrix, so I1 is equal to I1, I2 is equal to I2, this will be 1, I3 is equal to D3 ID, so the third entry will be D3, and I4 is equal to D4 ID. So this matrix is called C1 matrix, and this column vector is called I dash, and this column vector is called I old. And we also know that ID is equal to minus T1 I1 minus T2 I2 minus T1 IN naught. So we can express I1, I2, and ID in terms of I1, I2, and IN naught. So we will have a new column vector that will be I1, I2, and IN naught over here. Since I1 and I2 are present at both sides of this matrix, so I1 is equal to I1, I2 is equal to I2, this will be 1, and ID is equal to minus T1 minus T2 minus T1, and I1, I2, and IN naught will be present over here. So this transformation can be expressed in the form of an equivalent circuit. This was our original four node or four port network, and you can see I1 and I2 are two nodes which are connected to the generator. I3 and I4 are the two buses which are connected to the load, and this is the neutral node. Now this is our C1 matrix, and we know that I old is equal to C1 times I dash, and I dash is equal to C2 times I new. This is I dash, this is C2 matrix, and this is I new. So I old is equal to C1 times C2 times I new, and C is equal to C1 multiplied by C2. This is what I will show you soon. And now this is our C1 matrix, and the underlying equation behind this C1 matrix are these two equations, I3 and I4. So based on these two equations, we can draw an equivalent circuit. So this is the equivalent circuit which corresponds to the C1 matrix. Here, these are the first two nodes which are connected to the generator. There is no transformation in these nodes. And these are the two nodes which are the load buses, I3 and I4. So this is our load center, and this load current is equal to I3 plus I4. So here we will have I3 and here we have I4, and at this point we have D3 ID. So it means we have a transformer over here, and this is the primary current of this transformer, which is equal to I3, and this will be the turns ratio of this transformer. The secondary turns are 1 and primary turns are 3. So the current at the secondary side of this transformer will be equal to the primary turns divided by secondary turns multiplied by the primary current. So D3I3 will be the secondary current of this transformer. So that D3I3 is the current which is available over here. Similarly, D4I4 will be the current which is available at the secondary of this transformer, and the total current will be equal to ID. And this is our ground or neutral node. So this is the equivalent circuit which translates the C1 matrix, right? So this is C1 matrix, and the underlying equations behind this C1 matrix are I3, ID is equal to I3 is equal to D3 ID, and I4 is equal to D4 ID. And now we will transform this C2 matrix, and we will evaluate its equivalent circuit, which constitutes this C2 transformation matrix. So in this transformation matrix, we have ID equal to minus T1 I1 minus T2 I2 minus T1 IN naught. So this is the equivalent circuit of this C2 transformation. And this is our first bus, this is our second bus, and we must have three currents over here, T1 I1, T2 I2, and T1 IN node. So we will have a transformer over here, and the secondary of this transformer will have a current equal to T2 I2. This is the transformer which is connected to the first bus, and T1 is the primary number of turns, 1 is the secondary number of turns, and the secondary current in this case will be equal to primary turns divided by secondary turns multiplied by the primary current. Okay, so this is actually G2, this is actually G1. So by mistake, I have written G1 over here and G2 over here. So you can correct this by yourself. And this is T2 I2, this is T1 I1, and this is T1 IN node, right? So this is our neutral bus, and the current entering from this bus is equal to IN node. And here again, this will be equal to T1 ratio 1 transformer. And this, at the secondary of this transformer, we will have a current equal to T1 IN node. So these three currents will merge into this node, and we will have ID over here that will be actually flowing into this bus. The reason is that we have ID equal to minus T1 I1 minus T2 I2 minus T1 IN node. In that case, we had all the currents positive, but here you can see all the currents are negative. So all the currents will be entering this bus, and the resultant current ID will also be entering this bus. So the clear picture of these two figures can be seen in this book, right? So this is the power system analysis book, and you can see all the directions of the currents, the turn ratio of the transformers uh, over here as well. So this is the transformation C2, and we can write C equal to C1 multiplied by C2. So we have C1 matrix, right? So this is our C1 matrix. We have this C2 matrix. So we can multiply these two matrices to get overall C matrix, and C matrix will be equal to this matrix, and that will be 4 by 3 matrix. So we can also compare this C matrix with the one that we obtained in our previous lecture, right? So in our previous lecture, we obtained this C matrix directly, and you can see this is our I old, this is our I new, and I old is equal to C times I new. This is a 4 by 3 matrix, and the same matrix has been obtained by using this two-step process. Okay, so multiplying these C1 and C2 matrices, we get this C matrix. So this is the transformation which you can see I old is equal to C times I new, and I old is equal to C1 times I dash. Okay, so this is our I old, this is our C1, this is I dash, and also I dash is equal to C2 times I new, right? So I dash is equal to C2 times I new. This is our I dash, and this is our I new. So we can see I old is equal to C1, and instead of I dash, we can write C2 times I new. So I old is equal to C1 C2 I new, and C1 C2 is equal to C. So I old is equal to C times I new, which is written over here. So for voltage transformation, we will use opposite way, right? So this is our V dash, right? V1, V2, and Vd with respect to the neutral node, and that is equal to C1 conjugate transpose multiplied by V old. This is our V old, this is C1 transpose and conjugate, and after multiplication, this V dash will be equal to V1 and V2 and D3 conjugate V3n plus D4 conjugate V4n. So this is the first equation. V dash is equal to C1 conjugate transpose into V old. Now V new is equal to C2 transpose conjugate into V dash, right? So this is our V new, this is our C2 conjugate transpose matrix, and this is our V dash. So from equation 1, we can substitute this V dash into this equation, And V new will be equal to C2 conjugate transpose multiplied by C1 conjugate transpose multiplied by V old. So these two matrix multiplication terms can be combined together, and that will be equal to C1 C2 whole conjugate transpose, because C1 C2 whole transpose is equal to C2 transpose multiplied by C1 transpose. So we can write these two matrices collectively as C1 C2 whole transpose conjugate into V old, and this C1 C2 is equal to C matrix, so V new is equal to C conjugate transpose into V old. So these are the two expressions which we have obtained at the end. I old is equal to C times I new, and V new is equal to C conjugate transpose times V old. So that is all about our today's lecture, in which we have discussed in detail the interpretation of the transformation matrix C. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.